I'm not standing right in front of the camera, it doesn't focus right. Okay, so we want to talk about proteins, peptides. And the first thing we need to talk about is the amino acid structure of things. And that requires reviewing Fisher projections. It's been a while since we've worked with them. So you may have forgotten what they are and how to convert them into real structures. So amino acids are generally drawn as Fisher projections when there's just one of them. The carboxylic acid as the most oxidized carbon goes on the top of the Fisher projection. The side chain, whatever that side chain is, so in the case of CH3, it's Alanine. It's got a methyl group as its side chain. And then the standard amino acids that are present in mammalian systems are L amino acids. And what that means is that the NH3 group, or the NH3 plus group in this case, comes on the left-hand side, and the hydrogen goes on the right-hand side. So this is where the big L comes from. It's based on the nomenclature for the simple sugar. The simplest sugar is glyceraldehyde, and this is D-glyceraldehyde. And what the D tells you is that that OH group is on the right-hand side. So in the case of the amino acids, instead of having a hydroxyl group and a hydrogen, we have an ammonium group and a hydrogen, but the D and L still refer to the position of the one closest to the bottom of the Fisher projection. Right? In this case, there's only one chiral center. In this case, there's only one chiral center. So there is just a D isomer and an L isomer. You don't have to worry about the other ones. So the D system has the thing that isn't hydrogen on the right, and the L system has the thing that isn't hydrogen on the left. Always the most oxidized carbon on the top. So in this case, the most oxidized carbon is the carboxylic acid. In that case, it's the aldehyde. And then whatever else is present down at the bottom. So this is where the side chain goes at the bottom. But that's planar. So that's kind of a pain in the ass. It doesn't actually give us a good picture of what that actually looks like in 3D. So we need to convert to the dashed wedge structure. And the way to do that with the Fisher projection is to recognize that the things that are on the vertical are going back into the plane of the board, or behind the plane of the board. And the things that are on the horizontal are coming out of the plane of the board. And I refer to that as the bow tie conversion. Looks like a bow tie with the wedge structures. That's annoying because it means that almost nothing is actually in the plane of the board. The only atom in the plane of the board is this carbon. Which makes it difficult to work with. If we're going to make a peptide, we're going to be creating amide bonds from the carboxylic acid function of one molecule to the nitrogen function of the other molecule. It would be nice if we can get those into the plane of the board so that the molecule mostly is in the plane of the board. So after we do this bow tie conversion, we want to flop this molecule down in such a way as to put as many things in the plane of the board as we can. The other thing I should mention, I just did it and I didn't actually really talk about it, is amino acids in solution exist as Zwitter ions. Which means you've got a positively charged nitrogen and a negatively charged oxygen in the same molecule. And that's because the carboxylic acid function is quite a bit more acidic than the NH3 function. So if a proton comes off, the first proton that comes off the carboxylic acid function. You know that a COOH group is usually, right, a pKa somewhere around 5-ish. But when that COOH group has an adjacent nitrogen, the pKa of that drops closer to 2. And if you look on page 1193 and 1194 in the chart, you'll see that the pKa of those alpha carboxylic acids tend to be somewhere between like 1.8 and 2.5. So 5 was already going to be lower than the pKa of the ammonium group, and now it's even more lower because of the electron withdrawing nitrogen. If you look in that same table, you'll notice that the pKa of the alpha NH3 group is actually pretty comparable to what you would expect it to be for a general ammonium group. These pKa's are between 9 and 10.5-ish, right, which is exactly what you would expect for ammonium. So this is, if you round it to 2 and you round this to 9, this is 7 orders of magnitude more acidic than that, which means it comes off first. So anytime you're talking about amino acids in solution, you want to draw it as a COO minus and an NH3 plus, not as a COOH and an NH2. In the solid phase, when it crystallizes, probably crystallizes as the carboxylic acid here, just an NH2 group. But as soon as you put it in water, the more acidic proton is coming off, and the less acidic proton is not coming off, so you get a neutral species. So that's another kind of feature. So what we want to do is flop this into the plane of the board. And since I'm going to want to define this stereocenter as either being R or S, it's logical to flop it that way. So the hydrogen goes back behind, because then it'll be easy for me to look down the right bond. So if I flop it that way, then these two things go into the plane of the board. The hydrogen ends up going back. NH3 comes up. And now I can pretty easily determine whether that's an R stereocenter or an S stereocenter. This still isn't the way I'm going to want it in order to form bonds, because the NH3 group is not in the plane. And I'm going to be forming bonds from the amine group on one to the carboxylic acid on the other. So I'm going to actually want those two in the plane of the board. But this is the best way to look at whether that's the R or the S stereocenter. So which is it? Nitrogen has the highest priority over carbon. Hydrogen's always the big loser, right? This one has 2 oxygens attached, so it's 2. This is 3. And that's the S stereocenter. All but one of the common amino acids are S stereocenters. There's one exception, and it's not because the configuration changes, it's because the group priorities change. So one of the amino acids has a CH2SH here. This is cysteine. L-cysteine. It's got the same configuration around the chiral center. But now this carbon takes priority over that one because this carbon is bound to a sulfur, and that's only bound to oxygen. And even though that's bound 3 times to oxygen, one sulfur, because it's heavier, outranks the oxygen. So because of that switch, so that the side chain actually has priority 2, cysteine is the only common amino acid that's on that list of 20 common amino acids that has an R stereocenter. Right? But as I said, it's not because the configuration changes. It's still an L series amino acid. It just has a switch in the priorities because of the sulfur. The other amino acid that has the sulfur in it is methionine, but the sulfur is not directly attached to the beta carbon like it is here. So this is the beta carbon, this is the alpha carbon. The chiral center is at the alpha position, And then many of them have a CH2 group there. There are a couple of exceptions where that's not a CH2, but a lot of the amino acids have a CH2 group in the beta position. So a bunch of different ways of drawing the amino acid, but none of them are what we want. What we really want is we want to be able to write the nitrogen on the left, the carboxylic acid on the right, and have the side chain and the hydrogen be the groups that are not in the plane of the board. Right? So what we'd really like to do is we'd like to flap it like this way. So we have the NH3 there, and the CO2 minus here. So we're taking it like that, we're flopping those two things in, the hydrogen should be coming out, CH3 should be going back. And is that still an S stereocenter the way I drew that? Now we have to put ourselves back behind the plane of the board. Right, so we're looking down this bond, and nitrogen to carbon. If I'm looking the wrong way down the bond, it looks like it's going clockwise, but I'm looking the wrong way down the bond, so it's the opposite. So I can draw it like that, but I could also flip it 180 degrees. Actually, draw that out. And if I flip it 180 degrees, then it looks like that. That's more obviously S, correct? Because the hydrogen is pointing back. So it's either this way or this way that I am in fact going to want to draw my amino acids. And you can see that if the kind of vertex is pointing up, then the hydrogen is in the back. And if the vertex is pointing down, then the hydrogen is in the front. Make sense? So there's a bunch of different ways to represent these amino acids. If you were to write the amino acids out, right, just if I were to give you a quiz, I won't actually give you this quiz, but if I were to give you a quiz that just says, here are the codes for the 20 amino acids, write out the structures, this is how you want to show it. Because the side chain's in the plane of the board, so that would make it easiest to draw the side chain, and then you just slap this on the end of every amino acid. Right? Because every amino acid has this relative configuration of these guys. But when you're drawing it as a peptide, you want them like this so that your nitrogen and your carbon are in the plane of the board, so we can draw several amino acids across. So that's the first battle. How to draw the damn things to get the stereochemistry right, to get the ions correct. Because if you can't draw things properly, nothing you say about them will be true. Right? You have to get the structure right, otherwise you're done. The problem is over. So if I asked you, for example, to calculate the isoelectric point for a peptide, first you have to successfully draw the right peptide. And that requires knowing all the structures of the amino acids. I probably will ask you to calculate the isoelectric point of a peptide on the quiz. So indirectly, I'm going to be asking you to memorize all the amino acids. And if you keep them memorized, then when you take biochem and you have to know them again, then you'll already know them, and that'll be one thing you don't have to do. So they're charged, right? There are two things we generally are interested in knowing about peptides. We'd like to know what the charge status is at physiological pH. Right, so we'd like to know which groups are protonated and which groups are deprotonated at physiological pH. And we'd like to know what is the isoelectric point. The isoelectric point is abbreviated PI for isoelectric point. It is not a P function. Normally when you see that p, that means it's the negative log of something. This is not a p function. It's not the negative log of I. It's just isoelectric point is pi. Right? And it would probably be good if we knew what we meant. What is the isoelectric point? And that is the pH at which the molecule is net electrically neutral. Why is that important? Because there's a technique called electrophoresis, which you may already be familiar with if you've taken some biology labs, where you apply an electric field across a gel, which is usually either agarose or like polyacrylamide. Polyacrylamide if it's peptides, usually agarose if it's nucleosides. And you apply an electric field, and the molecules will migrate until they get to the point where they no longer have a net electrical charge, and then they'll stop. So you can separate different proteins based on their different isoelectric points. And that's one of the ways of purifying proteins. It is a royal pain in the ass to purify proteins, especially if you lyse the cell, so you're working with all the proteins in the cell. They're usually present in pretty small quantities, and many of them have very similar molecular weights or very similar isoelectric points. So we're interested at this pH when the molecule is net electrically neutral. Not all of the molecules will be net electrically neutral, right? But what will be true at the isoelectric point is the concentration of the +1 species will be equal to the concentration of the -1 species, so that those will cancel each other out. And if you remember way back in the first semester, in chapter 2, you may have done this problem because I assigned it. If I can find it. There's a problem that asked you, I think it's chapter 2, somewhere. Chapter 2 is the acid-base one, right? All right, well, I'm not finding it right now. Somewhere in there was a problem that asked you for methanol, right, which you know can act as an acid. Or as a base. Amphoteric. And if you know the pKa value for these two species, right, if you know that this pKa is approximately 15.6-ish, and you know that this pKa is somewhere around -1.8-ish, I'm not sure those are exact, but right, you can calculate the pH at which the molecule is neutral, where the concentration of this is equal to that. And the problem asked you for three things. It asked you at what pH is the concentration of these two species equal. It asked you at what pH is the concentration of these two species equal. And it asked you at what pH concentration of the negatively charged species equal to the concentration of the positively charged species. This is what we're interested in, right? How do we calculate the pH at which the +1 and the -1 ion are equal to each other? So let's take a look at that problem, since it's been a while, and you probably didn't do it anyway when it was assigned last semester. How will we answer those three questions? Proteins and peptides are generally separated two different ways. One by size, by using some size exclusion chromatography where smaller molecules will move more slowly than big ones, and the other is by charge, based on the pH at which the molecule is neutral, which is the isoelectric point. So if we understand this, we can apply it to the peptide. The top two problems are easier than the bottom problem. Why? What's special about the top two? What's that? They're all equilibrium.
Well, yeah, but like if they're part of the same reaction, so we could probably use the kind of.
I could write this one, right? CH3OH2 plus is in equilibrium with 2H plus or CH3O minus. What's the relationship between methanol and the oxide ion? It's a conjugate acid-base pair. And that's also true here, right? This is a conjugate acid, conjugate base pair. And you probably remember from general chemistry, if you have equal concentrations of the conjugate acid and the conjugate base, it's fairly easy to determine the pH. Using the Henderson-Hasselbalch equation. Do you remember what the Henderson-Hasselbalch equation is? You have an unfair advantage because you're taking analytical right now. So if the conjugate acid, conjugate base concentrations are equal, what can you say? So we can say for the methanol to methoxide equilibrium that CH3OH concentration is equal to CH3O minus concentration at a pH of approximately 15.6, which is the pKa of methanol. Make sense? We can do the same for the methyloxonium in equilibrium with methanol by writing it like this. Say that those two concentrations are equal. At a pH of the pK of that, which is approximately minus 1.8-ish. So at a pH of minus 1.8, those two concentrations are equal. At a pH of 15.6, those two concentrations are equal. But what we want to know is when those two concentrations are equal. And those are not a conjugate acid-base pair, and that makes it a little bit more difficult. So when you had this problem last semester, you probably did first two, and then you got stuck on C. I swear that's in there somewhere. I'll find it later. So how can we do that? Let's start by writing the equilibrium constant. That would be a good start. Can we define that equilibrium constant in terms of the pKa's? Can we actually get a numerical value for that equilibrium constant? Well, that overall reaction is the sum of this one I'm just going to write them as pKa1 and pKa2 so I don't have to write the species name out. So if you add those two reactions together, what's the equilibrium constant for this? What do you do to equilibrium constants when you add reactions? You multiply them. Enthalpies, right? Those state functions, you add them. With equilibrium constants, you multiply them. So the equilibrium constant for that is equal to Ka1 times Ka2. And I can replace Ka2 here with Ka1 times Ka2. So I'm not actually using numbers, I'm just using the variables. What was I looking for? I was looking for the pH where the concentration of the negatively charged species was equal to the concentration of the positively charged species. So if I set those equal, this cancels. And what I have is that the concentration of H plus squared is equal to Ka1 times Ka2. Right? That's a pretty easy equation that I did by just adding together the two functions, multiplying the Ka's. If I take the negative log of both sides, how can I simplify that? What's the negative? What's the log of something squared? Negative 2 times the log of H, or 2 times the negative log of H. And I want to break that up. This is equal to the negative log of Ka1 plus the negative log of Ka2. Because log of AB is equal to log of A plus log of B. And log of A to the B is equal to B log A. So we're using those two log rules to simplify this. If I bring the 2 over, I now have that negative log of H plus is equal to negative log of Ka1 plus negative log of Ka2 divided by 2. But that is pH, and that is pKa1, and that is pKa2. I determined that the pH is actually equal to the sum of the pKa values divided by 2, which in this case would be equal to negative 1.8 plus 15.6 divided by 2. And what's that? It's pretty close to 7, right? Really close to 7. Not exactly 7. That would make sense, right? Methanol is a neutral molecule. At a pH of 7, which is neutrality, you would predict that it would be mostly methanol and only a little bit of these two. Right? Because methanol can auto-ionize just like water can. But you would predict that these two concentrations are pretty damn low, right? And so the Kw for methanol, right, is probably the auto-ionization constant is probably similar to what it is for water. So we can apply that to our protein situation. I will probably at some point ask you to reproduce that derivation and prove that the PI, the isoelectric point, is equal to the sum of the two pKa's divided by 2. For a lot of different amino acids, though, there's more than 2 pKa values, because some of the side chains also have acidic or basic functional groups. Right? So there's a pKa for the side chain, there's a pKa for the carboxy terminus, there's a pKa for the amino terminus, and for peptides there might be multiple side chains that all have charged species. So let's look at a short peptide. Let's look at a tetrapeptide, and let's look at the one represented by those 4 letters. Every amino acid has a 1-letter code and it has a 3-letter code. So E is the code for GLU, which is glutamic acid. A is code for ALA, which is alanine. S is the code for serine, which is SER. And Y is the code for tyrosine. And you can look at those in the table. It'll give you the 3-letter code and the 1-letter code and the name. Right? And what you should be able to do is go from 1-letter code to 3-letter code to name to structure. So we're looking at glu-ala-ser-ti. So another way to write this would be glu.ala.ser.tir. And if you wanted the name, it would be glutamyl alanyl serial tyrosine. Which is annoying, right? We're not usually going to write out the name for a long peptide. For a tetrapeptide, it's okay. We can write it as glutamyl alanyl serial tyrosine. But for a long peptide, it's easier to go with the 3-letter codes. And for a really long peptide, that becomes annoying. You want to go with the 1-letter code. Right? So we'd like to do 2 things here. We'd like to write it, draw it as it appears at physiological pH. And we'd like to calculate its isoelectric point. On the final, you'll have a peptide. You'll draw it as it appears at physiological pH, and you'll calculate the isoelectric point. What is physiological pH, you biotypes? When we say physiological pH, what do we mean? No, not so much. Biology people haven't told you that. .4 is a number that's often used. It's the pH of like healthy blood that isn't suffering from acidosis or something. So when we say physiological pH, what we really are talking about is a pH of 7.4. At physiological pH, at a pH of 7.4, all side chains with pKa greater than 7.4 stay protonated, and all side chains pKa less than 7.4 are deprotonated. Two amino acids that have the basic side chain are arginine and lysine, ARG and LYS. Lysine is K, arginine is R. Because A was already taken, right? And as it turns out, L is already taken because leucine is L, so lysine has to get a different letter. That's why it's K. Tyrosine is Y because T is threonine. Right? There's multiple amino acids that start with T. So the basic side chains stay protonated. And the acidic side chains and those are aspartic acid and glutamic acid. Those have carboxylic acids in the functional group. Those are going to be deprotonated. Sometimes you'll see this written as aspartate and glutamate instead, because they're deprotonated, right? So in normal physiological systems, it's not glutamic acid, it's the glutamate ion, and it's not aspartic acid, it's the aspartate ion. So you'll see aspartate and aspartic acid used interchangeably. So we need to know what the side chains look like for these guys in order to write this structure. The tyrosine side chain is a CH2 attached to a benzene ring with a phenol. Right? The phenol is actually an acidic side chain too, not as acidic as aspartate or glutamate, but it is acidic. And if you look up the pKa of that function, for tyrosine, it's 10.1. Don't memorize the pKa values. I will definitely give you to those. Serine has the functional group CH2OH. Cysteine is the one that has CH2SH. And you can remember those by knowing that serine is the one that starts with S, so it doesn't have the sulfur in it. Just for maximum annoyance, right? It's cysteine, the one that doesn't have the S in the beginning of the name that has the sulfur in it. Serine and cysteine are easy ones to confuse. Alanine we've already looked at. Alanine is the one that has a CH3 as the side chain. And then glutamic acid, the side chain is CH2, CO2H. Got a pair of CH2 groups. Aspartic acid just has one. And you can find those in the table. Aspartic acid and glutamic acid are over on the right-hand side, right? So this one has a acidic functional group. We'd have to look up that pKa. And the pKa for that side chain functional group of aspartic acid, or sorry, glutamic acid is 4.3. pKa of this one is 3.7. Anybody want to tell me why the pKa of aspartic acid is lower than the pKa of glutamic acid?
There's less, like there's one less carbon separating it from.
That's closer to the nitrogen than this one is because there's an extra CH2. So this one's a little higher. So we know that at physiological pH, that's actually going to be deprotonated. It's written by convention. The N terminus on the left and the C terminus on the right. So there will be an NH3 group over here, and then there will be a CO2 minus group over there. So now we can embark on the process of writing the peptide. We have an H3N group, and then we have a peptide bond. Which is just a fancy way of saying amide. Peptide bonds are amide, right? And then we're going to have another side chain, and a CO group, and another peptide bond. And we're going to have another side chain, another CO group, right? And another peptide bond. So there's one amino acid here. Another amino acid there. A third amino acid here. And I'm going to start by writing everything fully protonated. So I've protonated my C terminus, I've protonated my N terminus. Now I want to put on the side chains. When the vertex is pointing up like this, is the hydrogen up or back? Back. So this hydrogen will be back. My side chain will be up. When the vertex is pointing down, the hydrogen's up. The side chain is back, so my CH3 for my alanine is back. So the molecule looks like that. That's with everybody protonated. The things I've circled in yellow are the protons that could come off. The side chains of alanine and cysteine, or serine rather, alanine and serine, have side chains that are neither acidic nor basic. Yes, the pKa of that serine is somewhere around 15, but in general we don't worry about that. That serine hydrogen is usually not coming off. Although actually in serine proteases, right, proteases that actually cleave other proteins, the serine hydrogen does come off because of where it is in the active site. So there are 4 things we have to worry about. We need to know the pKa of each of those. We already looked this one up. That one's 4.3, and we looked this one up. That one's 10.1. But we need to know the pKa of the COOH group, the alpha COOH group of tyrosine, because it's different for each amino acid. So we're going to look up tyrosine, and we're going to determine that the pKa of the alpha COOH group for that is 2.2. And we need to know the pKa of the N-terminus of glutamic acid. So we're going to look in the table for the N-terminus, the NH3 group, the alpha NH3 group for glutamic acid, and that's 9.7. So at a physiological pH of 7.4, who's deprotonated? That's less than 7.4. That's less than 7.4. But the other two are not, right? So these at a physiological pH of 7.4, those stay protonated. So if I wanted to draw it at physiological pH, I would need to take away that hydrogen, and I would need to take away this hydrogen. And I would draw it like this. What's the overall charge on the molecule at physiological pH? That's something we're usually interested in. What's the charge on the molecule? What does it look like at physiological pH? So not too surprisingly, perhaps, the functional groups that are deprotonated are the two carboxylic acids. And the nitrogen stays protonated, right? And so does the phenol, because the phenol is much less acidic than the carboxylic acid. So now how am I going to go about figuring out what the isoelectric point is? I don't really want to draw that molecule out multiple times because it's a pain in the ass. So what I want to know is when it's fully protonated, what's the charge? Right? Before I took those two protons off, when I had both the carboxylic acids protonated, what was the charge on the molecule? +1. So now I'm going to start writing equilibrium constants for this, but I'm going to write it without writing the whole damn chain out, because that would be a pain. And you can do that if you want, but it would be a pain. I'm going to say that the +1 species is in equilibrium with the hydrogen and the neutral species, and the KEQ for that is equal to Ka1, and that's the lowest Ka of the ones in the molecule. And then I'm going to say that the 0 species is in equilibrium with H plus and the -1 species, and that KEQ is equal to Ka2. -1 is in equilibrium with hydrogen ion plus the -2 species. That KEQ is equal to Ka3. And the -2 is in equilibrium with hydrogen ion plus the -3 species. So if I deprotonated everybody who could be deprotonated, this would be an H2N group, this would be an O- group, and my overall charge would be -3. Right? That's the most negative I can get it by taking all the protons off. And this is the most positive it can get when I take off none of them. So Ka1 is what? What's the most acidic? What's Ka2? What's the second most acidic? The next one off. And the next one, this one, and the last one. So in order, I take off the C-terminal one first. That's almost always true. And in fact, I think it is always true. Then I take off the carboxylic acid in the side chain. Then I take off the N-terminus, and then finally I can take off the phenol. Which of those two do I care about for calculating the isoelectric point? Do I care about all of them? It'd be a very bad idea for you to care about all of them. That's the most common mistake. The PI is not the average of all of the pKa's involved. I only care about these two because these are the two that involve the species that I'm trying to set equal to each other, which is the +1 species and the -1 species. Right? At the isoelectric point, there are going to be negligible concentrations of -2 and -3. It's basically going to be the neutral species in equilibrium with the +1 and the -1. So I really only care about that, and I can rewrite this equation as +1 is equal to 2 times A plus -1. The equilibrium constant is now equal to Ka1 times Ka2 is equal to A plus squared times the -1 species over the +1 species. And I'm setting these two equal. Which means that my hydrogen ion concentration squared is equal to Ka1 times Ka2. And if I take the minus log of both sides and rearrange it, pH is equal to pKa1 times pKa2 over 2. Which means 2.2 plus 4.3 over 2. So the isoelectric point of this peptide is quite acidic. At a pH of 3.25, this peptide, easy, will not move in an electrical field. It's got two acidic side chains here. One of them quite acidic, the other one not, and it has no basic side chains. So in practice, what you want to do always is you want to draw the completely protonated form of the peptide, figure out what its charge is, write down all the pKa's for all the possible protons that could be removed, either protonated basic side chains or carboxylic or acidic side chains. Right? And then you want to take each one off in turn. Right? All the ones that are lower than 7.4 will come off at physiological pH, and the ones above will not. So you can figure out what the charge is at physiological pH. And then you can determine which two equilibrium constants are the ones you care about, right? By figuring out which two have that neutral species in it. Right? Some proteins, where you protonate them, they might have a charge of +4, which means you don't even care about the first several equilibria because they're taking protons off to get to the +1 species. So let's take a break. It's 9:15, and then we'll come back and we'll do maybe another example of this, just to solidify it. And then we'll talk about, if you have an unknown protein, how do you start figuring out what that structure looks like?
Did you say we didn't have to memorize like the names of it? You said we didn't have to memorize the pKa values?
I will give you a table of pKa values. Do not memorize that. But you should know the names, the codes, and the structures so you can, so if I give you like a peptide written out in either the full name or the 3-letter codes, you should be able to do it. I won't require you to know the 1-letter codes. Next semester in biochemistry, you will have to know the 1-letter codes, but for now, the name, the structure, and the 3-letter code is enough.